Welcome everyone. This is the second video for our subject General Chemistry 1, Common Isotopes and Their Uses, Module 5. In this module, there are different isotopes with their important uses, which are listed on page 10 to 11. I hope you will study it and appreciate the importance of isotopes in our daily life. So we will discuss some more. Isotopes are atoms of the same element that have the same number of protons but different number of neutrons. There are three main subatomic particles. These are the electron with a symbol of E minus, proton, P plus, neutron, and 0. And remember that the number of protons is equal to the number of electrons and also equal to the atomic number. And that the mass number is equal to the number of protons plus the number of neutrons. And from this formula, we can derive the number of neutrons is equal to the mass number minus the number of protons. So we can use this to provide the answers to the blank spaces in this table below. Okay, here it is. So let me introduce the columns. These are for the isotopes and the atomic number, the atomic mass, also the mass number, the number of protons, the number of electrons, and the number of neutrons. For isotopes, we have carbon-12, carbon-13, and carbon-14, and also the nitrogen-14, 15, and 17. Okay, now let's do the answers now. So, for carbon-12 given are the atomic or is the atomic number 6. And remember that the atomic number is equal to the number of electron and equal to the number of proton. That means if you know one of this, you will know the other two. So we know the atomic number, so we will know the number of protons will be 6 and the number of electrons is also 6. The number of neutrons is here. It is equal to the mass number minus the number of protons. The mass number is 12 minus 6, the number of protons. So the number of neutrons is also 6. For carbon-13, the given is the protons. So protons is equal to the electron. That would be also 6. And the atomic number, which will also be 6. Okay. So how about the atomic mass or the mass number? The mass number is equal to the number of protons plus the number of neutrons. So that is 6 plus 7. The answer is 13. For carbon-14, the given is the atomic mass and the number of electrons. So the number of electrons is 6. So the number of proton is also 6. And the atomic number is also 6. What is the number of neutrons? The number of neutrons would be mass number, which is 14 minus 6. That will be equal to 8. Now, let's go to nitrogen. Nitrogen, the given is nitrogen-14, the given is atomic number 7. So we know the number of protons will also be 7 and the number of electrons will also be 7. What is the number of neutrons? This is mass number minus number of protons. The mass number plus number of protons or minus the number of protons, that would be equal to 7. Nitrogen-15 given as the number of proton 7, so that means electron will also be 7. Atomic number will also be 7, and the atomic mass, it is the number of protons plus number of neutrons. 7 plus 8, this will be 15. And then nitrogen 17, the Number of electron is 7 that is given. So the number of protons will also be 7, and the atomic number is also 7. Now, the number of neutrons would be equal to the mass number minus the number of protons. So that is 17 minus 7. That would be equal to 10. So that's it. It's easy to identify, okay, using these things to remember here, the formulas. Now, we said that isotopes are atoms of the same element. So here, carbon, these are atoms of the same element with the same atomic number here, but different number of neutrons. And of course, they have the same number of protons. For isotopes of nitrogen, so these are atoms of the same element with the same number of protons, but different number of neutrons. Okay, so from these isotopes, we will take one and get the uses. So we have carbon-14. Radiocarbon dating, also referred to as carbon dating or carbon-14 dating, is a method for determining the age of an object containing organic matter. That means it is originated from living organisms by using the properties of radioactive isotope of carbon. That is why the name is radioactive carbon. Carbon dating is used to determine the age of artifacts up to 50,000 years old. It cannot be used to date fossils of dinosaurs which are over 65 million years old. Other radioactive isotopes are used for that. Then, artifact is a general term for an item made or given shape by humans, such as a tool or a work of art, especially an object of archaeological interest. Half-life of a radioactive isotope describes the amount of time it takes half of the isotope in a sample to decay. So we will have the example of half-life. So for example, the half-life of carbon-14 is 5,730 years. So initially, if we have 2 kilograms of carbon-14, after 5,730 years, that is the half-life of carbon-14, half will remain. So from 2 kilograms, it will become 1 kilogram. It decayed to 1 kilogram of carbon-14. After another 5,730 years, from 1 kilogram, it decays to 1/2 kilogram. That means what is left is 1/2 kilogram of carbon-14. After another 5,730 years, from 1/2 kilogram, it will become 1/4 kilogram of carbon-14. Now, the mass here might be gram, might be tons, but it is the same process. It will decay into 1/2 after the half-life. Okay, and it goes on until nothing is left. Now, let's go to the solving problem. We have the formula to be used. We have A times T is equal to A sub 0 E raised to K times T, where AT is equal to the final amount, A sub 0 is equal to the initial amount, K is the rate of decay or exponential decay rate, and T is equal to time. Now we'll go to the problem. It says, a wooden artifact artifact from an ancient tomb contains 50% of carbon-14 that is present in living trees. Using the half-life of carbon-14, 5,730 years, calculate the age of the artifact. Now, from the problem, there is no initial amount. So we assume that the initial amount is 1 gram. So we will now start. And we will use, of course, the T that is 5,730 years, the half-life of carbon-14. So we have, in solving problem class, there are 4 steps. The first one is given, and then the required. Next is the formula and the solution. I will be giving 1 point for the given, 1 point for the required, 1 point for the formula, and 2 points for the solution. So 1 point for the process and 1 point for the final answer. So the problem will be given 5 points. Okay, let's start with the given. Remember that T is equal to 5,730 years, or the half-life of carbon-14. The initial amount we assumed as 1 gram. It is here. Now, we assumed that it is 1 gram. Here, we assume that it is 1 gram. And then what is required? In this first step, before we can calculate the age of the artifact, we need to solve for the rate of decay. So the formula, we'll just have to copy the formula that we have from above. That is equal to the final amount is equal to the initial amount times e raised to the decay rate times the time. Solution. Substitute the given data to the formula. Now, so AT is equal to 0.5 grams is equal to 1 gram E times raised to the time, which is 5,730 times the K, or the decay rate. Now, we can solve this by getting the natural log of values on both sides of the equation. So we multiply or get the natural log of 0.5 is equal to, again, natural log of E raised to the decay rate times, or the time times the decay rate. Now, where did this one, it's not here anymore. So what happened to it? Okay, now gram and gram here is cancelled. 1 here, there is no need to write 1 because it will not affect anyway, or you just, that means there is already 1 here. Okay, so we'll remove the 1 because it's not being used, or it will not affect the value here. So we cancel the gram, and then the 1 here is cancelled, or we do not need to write it anymore. Now, that is why we only have ln e raised to 5,730 k, or the rate of decay. Now, to solve this, we need to put this exponent here in front of ln e. We apply the power rule of logarithm. Take the exponent and write it as product of ln e. So we put this one here in front, 5,730 k times ln e. So, but ln e is only equal to 1, so it is cancelled out. Okay, the L and E is cancelled out. It is equal to 1. So what is left here, okay, is this one. The ln 0.5 is equal to 5730 K. Now, to easily get this K, now, we divide it with the same value as here, the coefficient of K. 5730 divided by 5730, and divide also the other side of the equation by 730. So what will happen is this 5730 will be cancelled, and what is left is K here. And then ln 0.5 and 5730. We can also rewrite this that the K is on the other side. Here, remember, you could rewrite this as ln 0.5 over 5730 equal to K. But it is the same with this, okay? This is more, is easier for us. This one, we are more familiar with this. So, now, ln 0.5 is equal to minus 0.693147. How to do that? To solve this, you need a scientific calculator. But if you do not have one, use your smartphone. Open your calculator app, then rotate or move your phone to a landscape position. The basic calculator will turn to a scientific one. Okay? So Kn in your scientific calculator, press the ln, then times 0.5. The answer should be negative 0.693147. There are some more numbers here, but we cut it this here at 7. And then divide it by 5730. The answer would be minus 0.0001200968. Okay? That is your rate of decay. So let's go now solving for the age of the artifact. Now from the problem it says that the final amount of the carbon-14 and the artifact is 50% of the initial amount. So here it is in the problem. A wooden artifact from an ancient tomb contains 50% of carbon-14. So that means it is for 50% of uh, left from the initial amount of carbon-14 in the wooden artifact. So that is why we will use it here. The final amount is equal to 50% of the initial amount. The amount of decay is the one that we just solved here. Okay? And again, we assume that the initial amount of carbon-14 is 1 gram. Then let's go to the required or the unknown. It is the time or the age of the artifact. How many years that it take to have 50% of the original amount? Formula, the same. AT is equal to A sub 0, E raised to the decay rate times the time, or in this case, the age. So we have now the solution. Substitute the given data to the formula. So 80 is 50% of 1 is 0.5 grams is equal to 1 gram. E raised to, this is the decay rate, and T is the age of the artifact. Again, we get the natural log of values on both sides of the equation. But before we do that, we cancel the G, okay? And we do not write the 1 anymore, okay? So we have natural log of 0.5 is equal to the natural log of E raised to the decay rate times the T. Then we write this exponent to the front here by applying power rules of logarithm, taking the exponent and write it as product of the ln e. Okay, we write it here and then multiply it to ln e, and ln e is 1. And to easily get this t, we have to divide it again with whatever the value of t here, or the coefficient of t. In this case, this is the decay rate. So divide both the values on both sides of the equation. So ln 0.5 divided by the decay rate, and then this decay rate t divided by this value. So canceled out. So what is left is t and ln 0.5 divided by 0, negative 0.000120968. Negative and negative, that means the answer is positive. The final answer is the age of the artifact is 5,730 years. It is 573 years in your module, but it is just a typo. The 0 was misprinted. So the correct answer is 5,730 years. Dating artifacts and fossils is the application of carbon-14, the isotope of carbon, to our society. Okay? I hope you understand. Thank you. And please subscribe to my channel.